Now that we've covered the main metabolic adaptation to endurance training in mitochondrial biogenesis, let's now discuss the other adaptations, next being fuel supercompensation. Now, as mentioned briefly, the primary fuel source for muscle is glycogen, and it is one of the fuel stores that supercompensates with endurance training. But first, let's talk about intramyocellular fat supercompensation. Now, to preface this topic, I want to ask, between these two individuals, who has more fat storage in their body? The sedentary obese subject or the endurance athlete? Now, most of you will clearly say that it is the sedentary subject on the left that has more fat storage in their body. But the thing is, the sedentary obese subject may have more adipose mass, but similar fat mass as the endurance athlete. Remember, fat is a fuel molecule. It circulates in the form of fatty acids, and it is stored in the form of triglycerides in various cells in the body, especially adipose tissue, but also in areas like muscle. In the sedentary individual, much of the fat is stored in adipose, and therefore they have large adipose tissue mass, as you can clearly see in the CT scan. But the endurance athlete may have just as much fat stored within the body, but just in different tissues, for example, like skeletal muscle. In fact, there are studies that show that highly endurance-trained individuals have increased fat storage within their body, but within muscular compartments as opposed to adipose when compared to sedentary obese individuals. And this has shown to be an adaptation in response to endurance training and is referred to as intramyocellular fat supercompensation, which again is essentially increasing fat storage within muscle cells. This just means you have more available fuel for your muscles to utilize during exercise that is localized to the muscle, that is immediately available in the muscle. Meaning the muscle does not have to rely on fat being broken down in, say, adipose cells and circulated as fatty acids and having to be taken up by muscle cells to be utilized as a fuel. It can just utilize the fat fuel molecules that are directly available in its cells. Now, intramyocellular fat supercompensation doesn't directly affect performance through improved aerobic power, like mitochondrial biogenesis does, but rather it supports performance that is super prolonged, whether it's continuous, like marathon running, or intermittent, like, say, during a soccer match. And it does this by increasing the preservation of the muscle's primary fuel source, which again is glycogen. Fat supercompensation in muscle does not mean that there is simply more alternative fuel and therefore the athlete can perform longer. When glycogen runs out, performance will stop even if there is plenty of intramyocellular fat available. So in summary, intramyocellular fat supercompensation may improve performance during prolonged bouts of exercise by simply increasing the capacity to preserve or spare muscle glycogen, which again is the muscle's primary fuel source. So let's take a look at some evidence of this adaptive response to endurance training as it relates to intramyocellular fat supercompensation. Now, this study represented here is also a histological analysis of muscle cells, and researchers applied a lab technique called oil red O staining, which incorporates a chemical to the muscle sample that stains lipid molecules, particularly triglycerides. And after the stain is applied, the density of the color red is assessed. And the darker the red stain, the more indicative of greater intramyocellular fat content. So here we have images that are representative of their findings. On the left column here, we have two images from pre-training. Image A are stained muscle cells at rest, and image C are stained muscle cells after a single bout of exercise. Again, these are images obtained prior to the training program. The second column here are images taken after 6 weeks of endurance training. Image B is at rest, and image D is following a single bout of exercise. Now, generally speaking, we can visually observe a darker red stain in the post-training column versus the pre-training column, indicating that with training, there is increased intramyocellular fat storage. Now, where we find the darkest red stain is in image D, which again is post-training muscle samples after a single exercise bout. Now you can see in image D versus C that there is greater fat content within the muscle cells following a bout of exercise after 6 weeks of endurance training. This means that not only is there greater resting fat storage in muscle, but there is greater mobilization of fat to muscle during exercise. Essentially, what this data is indicating is that as an adaptation to endurance training, there is greater storage of fat in muscle cells, in addition to greater mobilization of fat to muscle cells during exercise. So overall, this data demonstrates the increased storage and mobilization of fat to muscle following endurance training, and again, this accompanies improvement in glycogen sparing or preservation, especially during prolonged bouts of exercise, whether continuous like during a marathon or intermittent like during a soccer match. Now, briefly, as I don't want to spend too much time on this, the glycogen preserving effects of fat supercompensation in muscle is connected to an increased capacity for fat oxidation, and this is driven not only by an increase in intramyocellular fat storage, but also increased fat mobilization from other tissues in the body like adipose, as well as increased mitochondrial biogenesis, since fat oxidation occurs in the mitochondria and involves aerobic metabolism. Now, the data shows that endurance training can increase fat oxidation rates in muscle, and thus there is increased ability to utilize fat as a fuel, especially at higher intensities of exercise. This again would benefit prolonged exercise performance through the preservation of muscle glycogen, and not so much through fatigue resistance or improvements in the aerobic power. So now that we've discussed fat supercompensation in muscle, what about the supercompensation of the muscle's primary fuel source, glycogen? So muscle glycogen supercompensation simply means an increased capacity for muscles to store its primary fuel, glycogen. Also, to reiterate, remember glycogen is an endogenous carbohydrate store. You can think of it simply as a bunch of glucose molecules, which is also an endogenous carbohydrate, bounded together to be stored up as a large glycogen molecule for later use, like during exercise. So as I described earlier, muscle glycogen supercompensation is a training adaptation. So it's a specific adaptation to training programs that challenge glycogen stores consistently, or exercises within a training program that have a high utilization of glycogen, which is almost any type of exercise that you might do that is high intensity in nature and exhausted to some degree. So as you can see here, muscle glycogen supercompensation is multifactorial. So as I mentioned before, this figure is just the underlying mechanisms of muscle glycogen supercompensation as a result of training. So the two factors that contribute to this is, one, increased muscle glucose uptake, which would in turn increase glucose availability to form glycogen with. Number two is increased rate of glycogenesis. So if you don't remember this term, make sure you know it before the exam. Glycogenesis, formation of new glycogen. And so what's mediating this process of increased rate of glycogenesis is an increased glycogenic enzyme activity. What else this figure shows is that all this is largely mediated by increased insulin sensitivity, which simply means there is much more efficient interaction between insulin and its respective receptor, the insulin receptor. So with more efficient interaction, you have more efficient signaling, and these signals result in increased glucose uptake through the GLUT4 transport system, and increased glycogenic enzymes, which again are the enzymes that catalyze glycogenesis. So all together, increased insulin sensitivity as a result of chronic training results in muscle glycogen supercompensation. So with that being said, it is clear that endogenous carbohydrate storage and availability is integral for exercise performance, in particular endurance performance. And with that, we also have to understand exogenous carbohydrate intake, or carbohydrate nutrition, in other words, is also very important, because the exogenous carbohydrates that you consume, say on a daily basis, influences how much glycogen is being stored within the muscle. So training only increases the size of the fuel tank, but the gas within the fuel tank, the fuel within the fuel tank, is what you consume, what you put into it. So carbohydrate nutrition is a very important aspect of sports nutrition and human performance science. So let's get into certain topics related to carbohydrate sports nutrition. one of the topics that I want to talk about is carb loading. So one of the reasons I want to talk about carb loading in this class is because I can bet that most of you, if not all of you, have heard about it, read about it, or even talked about it. It is quite prevalent in the athletic community. It is adopted by many athletes to fuel their muscles prior to competition. However, the thing is, it is quite often misapplied, and this is likely enabled by a very poor understanding of the science underlying carb loading and how it manipulates your muscles' metabolism/physiology. So let's define carb loading by looking at its intention or purpose. And as you can see right here, it is to acutely or immediately and temporarily supercompensate muscle glycogen, to temporarily and immediately increase the size of your glycogen fuel tank that we call muscle. Okay, so this is a temporary and immediate overfueling effect. Can we do this through what we call a carb loading strategy, nutritional strategy? The answer is generally yes, you can. So the next set of questions we want to answer is, how should you carb load and how does it work? In other words, how do you apply carb loading strategies and what is the science underlying those strategies? So I want to refer you to this clip right here. This is a clip from one of my favorite TV shows, The Office, and this is the main character, Michael Scott. And in this scene, he is slamming down a bunch of carbohydrates in the form of fettuccine alfredo right before a 5K. He is doing this with the mindset that this quote-unquote carb loading is going to fill up his fuel tank, his muscle, to maximize the subsequent 5K performance. Is this the way to carb load? Is this evidence-based practice? I think this goes without saying. No, it is not. So let's go ahead and clear up some misperceptions on carb loading, because this, although it is satire, it is not too far off from the perspectives that many people, especially in sports, have on how carb loading works and how carb loading should be applied. So in order for us to understand the proper application and implementation of carb loading, we first need to understand the science underlying carb loading strategy. Let's first take a look at how glycogenesis is regulated. What are the inducers or stimuli for glycogenesis, again, the formation of glycogen, and what are the inhibitors or suppressors of glycogenesis? So what turns it on and what turns it off? When we understand this, we would have a better understanding of how carb loading interacts with this regulation of glycogenesis. So first, let's focus here. This is an enzyme called glycogen synthase, and you can sort of tell by the terminology what this enzyme does. So synthases are enzymes that catalyze reactions that synthesize something. Synthesize, for example, a large molecule. So glycogen synthase is an enzyme that stimulates the synthesis or formation of glycogen, i.e. glycogenesis. So glycogen synthase catalyzes glycogenesis. So as I said in the previous slide, glycogenesis is basically taking multiple glucose molecules, these are small carbohydrate molecules, bonding them together to form a large glycogen carbohydrate molecule that is stored within cells like the muscle cell. So it's not converting glucose to glycogen, it is taking a bunch of glucose, putting it together to form a large carbohydrate molecule, glycogen. That is what glycogenesis is. I just want to clear that up. So the activity of glycogenesis in a cell like a muscle cell is largely determined by the activity of glycogen synthase, in that when there's increased glycogen synthase activity, there is more glycogenesis happening and vice versa. So this is the target of regulation. So what are the things that regulate glycogen synthase activity and therefore glycogenesis activity? First, what is the suppressor or inhibitor of glycogen synthase and therefore inhibitor of glycogenesis? That is glycogen replenishment. So when the muscle cell is full of glycogen, the tank is full of fuel, this is going to inhibit glycogen synthase activity and therefore decrease glycogenesis. This makes sense because if the tank is full, there is no reason to put more fuel in the tank. So this is essentially saying we do not need more glycogen in the cell. So what is the factor, the regulator, that does the opposite? What factor increases glycogen synthase activity and therefore ramps up glycogenesis within the muscle cell? Well, it will obviously be the opposite of glycogen replenishment, and that is glycogen depletion, or when there's a significant amount of glycogen depleted within the cell. So, for example, after exhaustive exercise. So this would be stimulatory to glycogen synthase activity, which would then increase the rate of glycogenesis, formation of more glycogen. And this, again, makes sense, right? When you utilize your fuels, that automatically is going to trigger the mechanisms, glycogen synthase and glycogenesis, to put more fuel in the tank, more glycogen in the muscle cell. So one important detail that you must remember to understand carb loading from a scientific basis is that the more glycogen that is depleted, the greater the activation of glycogen synthase. This is the target of manipulation in carb loading strategies, meaning the initial part of carb loading before you actually load your cells with carbs is to actually deplete your muscle cells of carbohydrate stores. You have to deplete your muscles of glycogen. The reason you do that is to hyperactivate this enzyme, glycogen synthase. And in so doing, this drastically increases the potential for your muscle cells to form glycogen as long as glucose is available. So glucose will become available after you deplete your muscles of glycogen when you consume dietary carbohydrates. So when you consume dietary carbohydrates, this increases glucose circulating in your body, making it more available for the muscles to form glycogen with. And because glycogenesis potential is so high, because glycogen synthase activity is so hyperactive, you're going to have a whole lot of glycogen formation happening. A whole lot of glycogen formation happening to the extent where you may be able to overfuel your muscle cells with glycogen. In other words, acutely supercompensate glycogen, more glycogen than what your muscle's capacity for glycogen storage is. So with that being said, you now have a general understanding of how evidence-based carb loading strategies would work. As you can see, the best way to maximize muscle glycogen levels, say before competitions, is to initially deplete your muscles of glycogen. Now, there are two ways to do this. First, you utilize or deplete the existing glycogen within the muscle by doing exhaustive exercise. The other way you can do this is by restricting carbohydrates through your diet so that you don't provide substrate for your muscles to form glycogen with. Most carb loading strategies, as shown here, this is called a depletion taper technique, use a combination of both initially within this strategy. So as you can see in day 1, which is 7 days before competition, this is when the carb loading strategy begins. And day 1 is highly focused on depleting your muscle cells of glycogen. So like I said before, you could do that by exhaustive exercise. So in this case, this is just an example, 90 minutes exhaustive run to deplete glycogen stores. And then lower your carbohydrate intake. You don't want to go on like a zero carb diet. That's never really recommended for especially endurance athletes, but you just lower it relative to what you normally would consume. So here I just put moderate carbohydrate diet as an example. So you are exhausting your muscle cells of the glycogen, and you're not providing more carbohydrates or glucose to form glycogen with. So with that being said, all that is happening within your muscle cells is hyperactivity of glycogen synthase. Not a lot of glycogenesis is happening because there's no glucose or very little glucose available to form that glycogen with. So within days 2, 3, and 4, you start to taper down your exercise, hence the taper technique here. You taper down your exercise in terms of duration from like 90 to like 40 minutes a day. This is again an example. And you continue with your relatively lower carbohydrate intake, again, relative to what this athlete would normally consume. So the first 4 days is predicated on depleting the muscle or the muscle cells of glycogen. So from a scientific perspective, you would say that the first 4 days of this carb loading strategy is to hyperactivate glycogen synthase, priming the muscle for extreme glycogenesis when glucose becomes available from your diet. So that's where 5, 6, and 7 come into play. Days 5, 6, and 7 rather. This is when the actual carb loading occurs. This is when you consume a high carbohydrate diet relative to what you would normally do. And here you taper down from 40 to 20 minutes a day, so you're not utilizing the glycogen that is forming within your muscles at a very, very high rate. So you reduce, you taper down your exercise, the utilization of your muscles' glycogen. On day 7, you continue with the high carbohydrate intake, and you don't do really any exercise because you don't want to utilize the glycogen that is forming at a very rapid rate. So what the intention of, or rather the goal of this depletion taper technique, which is a common carb loading strategy, is by day 7 or right before competition, you have overfueled your tank called your muscle cells. You have overfueled it with glycogen because glycogen is the primary fuel source for exercise during competition in this example. So on day 8, just another detail is that you would obviously maintain your carbohydrate intake because this is obviously the day of competition. So you would want some additional carbohydrates introduced through your diet on the day of. But as you can see, conceptually, this is not reflective of what most people think carb loading is. It's not just about consuming tons of carbs. So obviously, if you already had a full tank of glycogen, and then the Thursday night before the football game on Friday, you just consume a crap load of carbs, you are probably not going to overfuel or supercompensate your glycogen stores. Why? Because you have done nothing to prime your muscles to form glycogen at a very high rate. In other words, your muscle cells do not have hyperactive glycogen synthase. So again, conceptually speaking, all effective evidence-based carb loading strategies should begin with some amount of days of glycogen depletion, again, through exhaustive exercise and or through moderation of carbohydrate intake. Okay, so depletion first, then you load it up. So that is the key to effective evidence-based carb loading strategies. Depletion taper technique is just an example, and you can set it up various ways. And this is, again, just an example. From a practical standpoint, as you can see, this is not going to work for a lot of athletes, especially team sport athletes that have frequent competitions throughout, say, the week or the month. So this would only work for certain athletes with less frequent competition. So this is why endurance athletes or track and field athletes adopt these practices. Mostly endurance athletes, because they don't have frequent competition. They can afford to do a week's worth of carb loading. But we have to understand that carb loading is simply a technique for athletes to use to make sure that they have a full tank of gas before their competition. But what is most important is their overall nutritional programming, which heavily involves the manipulation of exogenous carbohydrate intake. So for any performance nutrition program to be effective for an athlete or an individual who is training, it needs to be goal-based, and it also needs to be prescription-based, meaning it has to have some objectivity to it. So with that being said, we have identified in the science 3 major variables for nutrition programming. Now, there's obviously other aspects of nutrition other than carbohydrate intake, but since we're on the topic of refueling and maximizing glycogen stores for an athlete, we're going to stick on the topic of carbohydrate nutrition. So the 3 types of sports nutrition variables that have been heavily researched are type, timing, and quantity. So specifically in relation to carbohydrate performance or sports nutrition, for type, we can talk about the different ways to characterize the dietary carbohydrate. So for example, you can characterize the dietary carb as complex versus simple. We can characterize it by its glycemic index, or just simply the source, the food source for that dietary carb. The other one is timing. This is very specific to performance nutrition. So for example, when do you consume those carbohydrates, or the dosage of carbohydrates relative, say, for example, your workout or competition, pre, mid, post, for example. Quantity is referring to how much carbohydrates do you consume, say, before and after workout or throughout the entire day. So let's talk about some of the literature, the scientific literature that covers these 3 factors that outline carbohydrate nutrition programs. So one thing we have to understand first is that carbohydrate nutrition programming, so how we manipulate the time, timing, and quantity, in other words, how do we program these three variables into a carbohydrate nutrition strategy, is completely predicated on this, on how to best optimize glycogen resynthesis. In other words, in more lay terms, how do we best optimize muscle refueling? So the research shows that muscle refueling, say on a daily basis and throughout a training program, can be influenced by the type of carbohydrates you consume, the timing of the carbohydrate intake, and the quantity of carbohydrate intake. So let's go ahead and dive into these. So one point of emphasis that we have to understand is that dietary carbohydrate intake will always be a key factor for muscle refueling or muscle glycogen replenishment. And therefore, it's a key factor when it comes down to performance recovery, because in practical sense, when someone is training, they're doing repeated bouts of exercise. So obviously, dietary carbohydrate intake or the programming of dietary carbohydrate for an athlete is going to be critical because the athlete is likely depleting muscle glycogen every single day or very frequently throughout the weeks. So to ensure that the athlete has optimal performance not only during training but also during competition, we have to make sure that their carbohydrate intake is optimized as well, for the sake, again, of muscle refueling. Okay, we do not want the athlete to have an empty tank anytime he or she is training or competing. So going back to the three variables, time, type, and quantity, let's get a little bit more specific. We want to take a look at total daily intake as part of the quantity variable. We want to look at post-exercise timing of carbohydrate intake, so after you deplete your muscles of glycogen to some extent, and the type of dietary carbohydrates. So again, this is all predicated on maximizing muscle refueling. So as you can see in this third bullet right here, it says total daily intake is the most important factor for performance recovery following exhaustive exercise. This is the same thing as saying total daily intake is the most important factor for muscle refueling, for muscle glycogenesis, and restoring muscle glycogen following exhaustive exercise. So glycogen depleting exercise. Now, let's take a look at the scientific literature that uncovers the question of what this total daily intake looks like for the optimization of muscle refueling and therefore performance recovery. So we turn to what we call a position stand. So position stand is written by multiple researchers within this field who authored this paper and make a position on a particular research question. For example, what is the optimal total daily intake to maximize performance recovery in athletes who do exhaustive exercise? So within this position stand, it was stated that based on the literature and the research, 6 to 12 grams per kilogram of body mass per day would be the optimal range for carbohydrate intake, again, for the purposes of maintaining muscle glycogen levels to make sure that muscles refuel properly after training bouts. You can Google this position stand by just typing in some keywords. Type in carbohydrates, position stand, Kirksick et al., 2017. Journal of the International Society of Sports Nutrition, or JISSN. This is a free access journal, so you can pull up this paper and it's going to have a lot of good evidence-based practical information in there for you as it relates to carbohydrate nutrition strategies. So again, 6 to 12 grams per kilogram body mass per day for optimum recovery and maximizing muscle refueling. This is again only pertinent to athletes. This is not relevant for just your everyday individual. Clearly, this is above the RDA for carbohydrate intake. So I believe the RDA is about 130 grams per day. So if you think about a typical 80 kilogram individual, even at the lowest range, I mean, that's what, 480 grams of carbohydrates per day. That's significantly above the RDA. So make sure you communicate, you disseminate this information with context. You can't just say, I learned in school that you should eat 6 to 12 grams of carbohydrates per kilogram of your body mass per day, and say, oh, it's healthy for you, oh, it's good for you. You have to put it into context. This is for athletes or for highly active training individuals who deplete glycogen frequently throughout the week. And this is, again, only predicated on maximizing performance to ensure recovery of your muscles' glycogen, replenishment of your muscles' glycogen. Okay, so if you're just an everyday individual, sedentary, maybe works out like 1 or 2 times a week, 30 minutes each time, this is not relevant for that person. So always keep that in mind. Make sure you maintain the mindset that everything needs to be disseminated with context. Now, moving forward, let's turn our focus to another important variable in carbohydrate performance nutrition programming, and that is timing. And as I mentioned earlier in the prior slide, I want to focus the details regarding carb timing on specifically post-exercise consumption. And the reason I would like to focus on post-exercise carb intake is because there's a prodigious amount of research that shows the positive impact of post-exercise carb intake on muscle glycogen refueling during recovery periods, in particular short recovery periods such as less than 8 hours, which would obviously be pertinent to individuals like athletes in the meat of their season or off-season training, or someone who is training recreationally with high intensity and frequency towards a particular fitness or performance goal. Now in this slide here, I present results of an examination of multiple studies that investigated the relationship between the amount and rate of carb intake post-exercise on muscle glycogen refueling rates during recovery. If you can turn to this graph right here, the y-axis, as you can see, represents muscle glycogen resynthesis rate, or simply muscle refueling rate. And the x-axis here represents the post-exercise carb intake dosage per hour in the units of grams per kilogram body mass per hour. So first, let's focus on the data points represented by the blue aqua color, as you see right here. Now, this study took the different carb intake dosage rates across multiple studies and plotted each one against the average muscle glycogen refueling rate observed in response to that carb intake. Now, this is again reflecting post-exercise recovery periods. So as an example, if you take this particular point right here, subjects who consume roughly around 0.8 grams per kilogram body mass per hour post-exercise exhibited a refueling rate of about 12 millimoles of glycogen per kilogram of muscle per hour. So when placing a best line fit on this plot of data points represented by the blue aqua color, we can see that there is generally a positive linear relationship between post-exercise carb intake dosage and rate and muscle refueling rate. So just to put this all together in summary, this analysis showed that within an 8-hour recovery window, which is relatively short, post-exercise carb intake greater than 1.2 grams per kilogram body mass per hour appears to be optimal for muscle glycogen refueling, and theoretically this should translate to optimal performance recovery. So if we take a practical example of an 80 kilogram athlete, this athlete would consume carbs post-exercise at a rate of 96 grams of carbs per hour. Now this can be in the form of simple carb sources like a sports drink, mixed with carbs from full meals or snacks. A little more on the type of carbs later in this lecture series. So keep in mind, this data represented by the blue aqua color only represents the refueling rate in response to consuming only carbs post-exercise, so with no other nutrients co-ingested. So the next question this analysis addressed was how muscle refueling is impacted by carbs when co-ingested with other nutrients, such as protein/amino acids. Now, this data is represented by the purple color. So within each of these multiple studies, subjects consume carbs at varying dosages post-exercise together with some dietary protein. So it was a co-ingestion of carbs and proteins at varying amounts. Now, the findings from this analysis were interesting because it showed that one would achieve the same muscle refueling with a lower post-exercise carb intake rate when it is co-ingested with protein. So specifically, you can achieve similar refueling rates with a carb intake of about 0.8 grams per kilogram body mass per hour with protein co-ingestion compared to a carb intake of about 1.2 grams a kilogram body mass per hour without co-ingestion of protein. So it appears there is some positive synergy between protein and carb intake post-exercise as it relates to muscle glycogen refueling. Now, this has been theorized to be largely mediated by more efficient absorption of glucose that comes from the carbs that you just consumed and muscle glucose uptake when free amino acids from the dietary protein that you consumed are also present. So just as a simple summary of this comprehensive analysis on post-exercise carb intake and muscle refueling for individuals like athletes with frequent training bouts or competitions throughout the week, with relatively short recovery windows, so a high need for rapid muscle glycogen replenishment, here are some takeaways from this analysis. So post-exercise carb intake of 1.2 grams or greater per kilogram body mass per hour appears to optimize muscle glycogen refueling or replenishment during recovery periods. And this should translate to more efficient performance recovery. And this dosage is especially critical, at least within the first 4 hours post-exercise. Secondly, post-exercise protein intake of about 0.2 to 0.4 grams per kilogram body mass per hour, co-ingested with carbohydrates, may improve muscle glycogen replenishment when post-exercise carb intake is limited to less than 0.8 grams per kilogram body mass per hour. So protein co-ingestion with carbohydrate intake of greater than 1.2 does not appear to enhance muscle glycogen replenishment any further. So what this is ultimately saying is that co-ingesting protein with a lower carb intake of 0.8 grams elicits similar muscle glycogen refueling as higher carb dosages without protein co-ingestion. Now, this information right here presented in the second bullet or the sub-bullet is a bit more practically relevant since for most athletes, post-exercise nutrients consist mainly of protein and carbs. So in most cases, athletes would not need such a high dosage as 1.2 since they are likely consuming protein with their carbs. For example, Gatorade Sports Science Institute does some fantastic research on this, which ultimately shapes the design of their products. So you will see products that have a somewhat decent mixture of carbs and protein for their post-exercise nutrient products. Now, going back to the whole concept of staying within context, this information that we presented here in the last two slides is really not relevant for those who engage mostly in strength training, as typical strength training bouts are not very glycogen depleting types of workouts. So on average, muscles are still about 75 to 90% full of glycogen. Of course, this is just an estimate and would depend on so many different factors. But on average, most individuals engaged in a resistance training program would not need to go to extreme measures in terms of post-exercise and even daily carbohydrate nutrition. So all the data that we've presented so far is really pertinent to an athlete, someone who practices every day, someone who trains every day, someone who competes frequently throughout the week. So this is not to say that carbs are not important for those in resistance training. However, I don't want you guys to get that perspective from all of this. It is still important. You still use muscle glycogen, but you're not utilizing it on average to the same extent as a high performance athlete. So moving on to our next nutrition programming variable, let's take a look at the effects of dietary carb type on muscle refueling, especially during recovery periods. So this information here adds another layer to the timing details I discussed previously. So the question is, what type of carbs post-exercise would optimize muscle glycogen refueling and therefore performance recovery? So the study presented here focused on comparing two types of carbs classified by the glycemic index. Now, to briefly explain what that is, the glycemic index is a general measure, and it's a very general measure, of how fast blood glucose rises in response to consumption of a particular exogenous carbohydrate or a dietary carbohydrate. For example, a dietary carb that is high glycemic is generally one that is digested and broken down into individual glucose molecules at a relatively high rate, and therefore will be absorbed into blood circulation faster, creating something like a glucose spike, if you will. Now, examples of high glycemic carbs include foods with dextrose in it, which is basically another term for glucose, which would obviously bypass digestion since it's already glucose. So this would raise blood glucose levels very, very fast upon consumption. So as for low glycemic index carbs, these are typically larger carb molecules, often called polysaccharides, that generally take longer to digest and to be broken down into smaller constituents, glucose. Therefore, glucose would rise in the blood slower. Now, there is less of a glucose spike, if you will. An example of low glycemic carbs, which are also generally referred to as complex carbs, which is not too accurate of a description, but either way, an example would be carbohydrates found in foods like oatmeal. These large carb molecules are called again polysaccharides, while the high glycemic carbs like dextrose or glucose mentioned earlier is referred to as a monosaccharide. Okay, so let's first go over the experimental design of this study as shown on the left side here. At baseline, subjects came into the lab and underwent a muscle biopsy, and the muscle samples were used to test glycogen levels within the muscle. Now, the researchers ensured that the muscle cells were fully replenished with glycogen before the biopsy, and they did this by instructing subjects not to exercise for a few days and by consuming a high-carb diet. So next, the subjects underwent in the laboratory a glycogen depleting exercise protocol, which is essentially a run till exhaustion protocol. In other words, subjects were asked, aka forced, to run until they hit the wall. Afterwards, subjects were split into two separate treatment groups. One group consumed high glycemic carbs like dextrose, and the other group consumed low glycemic carbs immediately after this run. Total carb amount and timing was controlled between the two groups. Then a series of muscle samples in each group for each subject were collected during the recovery period, and muscle glycogen levels were compared between the two groups. Now, as you can see in this graph on the right, the group who consumed high glycemic index carbs post run to exhaustion had significantly greater muscle glycogen at any given time point during the recovery period. This implies that they had greater muscle glycogen resynthesis rates. In fact, within the 10-hour period post-exercise, the high glycemic group had near full replenishment of muscle glycogen, whereas the low glycemic index carb treatment had only partial glycogen replenishment. As you can see by this data and also other studies that demonstrate similar outcomes, high glycemic carbs, at least in the immediate post-exercise time frame, would be optimum for muscle glycogen refueling. So far, we know that 1, daily carb intake should be roughly 6 to 12 grams per kilogram body mass per day. 2, post-exercise carb intake dosing should be around 1.2 grams per kilogram body mass per day, or 0.8 if consumed with protein. And 3, immediately post-exercise, high glycemic carbs would be most advantageous. Again, these are evidence-based recommendations for the purpose of maximizing muscle glycogen refueling in athletes or those who train frequently and intensely and performs muscle glycogen depleting type of training. So with that as a summary thus far regarding carbohydrate nutrition and muscle refueling, let's continue on and explain why higher glycemic index carbs immediately post-exercise resulted in greater muscle refueling than lower glycemic index carbs. So as you can see here, the answer is greater insulin response. There is greater insulin response following the high glycemic index carb treatment because there's a greater rise in blood glucose levels. Remember, insulin secretion is proportionate to the level of glucose rising in the blood. So also remember, insulin is a hormone that not only stimulates glucose uptake, but also glycogenesis in cells such as muscle cells. So together with a rapid rise in blood glucose from the rapidly digesting and glucose liberating carbohydrate that you just consumed, there is much more glucose available in the muscle or for the muscle to form glycogen with, and greater activity of glycogenic enzymes to catalyze glycogenesis, and that is largely mediated by the insulin. Now, the last question we want to address in regards to carbohydrate nutrition and muscle refueling is, does consuming carbs immediately after exercise influence glycogen replenishment in comparison to a delayed consumption? So should you consume carbs as fast as you can post-exercise instead of delaying it for the sake of muscle refueling? That is the general question. So let's take a look at this experiment here. On the y-axis, you have muscle glycogen synthesis, and on the x-axis, you have 2 time frames post-exercise during which times muscle glycogen levels were tested. The red bar here represents the results for subjects who consume carbs immediately after exercise, while the blue bar represents subjects who did not consume carbs until 2 hours post-exercise. So immediate feeding, delayed feeding post-exercise. So when looking at the data during the 0 to 2 hour time frame here, the group who consumed carbs immediately post-exercise showed significantly greater muscle glycogen synthesis as the group who did not consume any carbs within this time frame. This is obviously an expected outcome because this group had no carbohydrate intake while this group had carbohydrate intake to refuel the tank. So what is interesting is that in the 2 to 4 hour time frame post-exercise, the group who consumed carbs immediately post-exercise, which was 2 hours prior to this testing time frame, had similar glycogen synthesis versus the group who consumed carbs within this time frame at the 2 hour post-exercise mark. So if you add these bars together versus these bars right here, you can clearly see that delaying your first carb intake post-exercise can negatively impact muscle refueling. So the takeaway is that there should be some carb intake immediately post-exercise to maximize glycogen refueling. Now, to layer on top of the info presented in the last slide, we now know that the immediate consumption of high glycemic index carbs post-exercise would be advantageous for refueling as opposed to delayed carbohydrate consumption post-exercise. So next, let's explain the mechanisms underlying this timing effect, explaining why consumption of high glycemic index carbs immediately post-exercise is most advantageous for glycogen refueling in the muscle. Now, this is a multifactorial explanation. So first, consuming high glycemic index carbs will result in a glucose spike in the blood, and this will be followed by an insulin spike in the blood. So also, we know from exercise physiology that the cardiovascular system is going to adjust blood flow towards active muscles during exercise. And this increased muscle blood flow will also remain elevated post-exercise for some time, especially in the immediate post-exercise time frame. So meaning immediately post-exercise, muscle blood flow remains elevated. So not only do you have a lot of glucose and insulin circulating in the blood flow is circulating towards the muscles that were active during exercise. These are the muscles that are depleted of glycogen. So in addition to this, the GLUT4 transport proteins, which are responsible for glucose uptake, are highly active in those exercised muscles because of the insulin signaling and also due to the fact that muscle contractions also stimulate these GLUT4 transporters. So immediately post-exercise, these GLUT4 transporters are very active in those previously exercised muscles. So altogether, you have glucose and insulin spikes in the blood, you have elevated muscle blood flow, you have a lot of GLUT4 transport activity, and thus you have a prime situation for muscle glucose uptake as well as glycogenesis, glycogen formation. And these effects diminish with time after exercise, so the immediate post-exercise time frame is essentially a window of opportunity to consume your carbs to maximize glycogen refueling. So now this figure here simply provides a general visualization of how improper or inadequate carbohydrate nutrition during training can influence refueling over repeated bouts of exercise and ultimately performance, not only during training, but perhaps a future competition. Now the blue line represents proper carbohydrate nutrition with adequate carb intake, and the red line represents inadequate carb intake. And these little green guys right here represent exhaustive exercise bouts. And on the y-axis, you have muscle glycogen levels, and x-axis is a time spectrum. So as you can see by this figure, Inadequate carbohydrate nutrition will have a negative effect on muscle glycogen levels over repeated bouts of exhaustive exercise. So, over time, this will leave one with an empty tank after repeated sessions of exhaustive exercise. And this could also be limiting to one's performance during each of the subsequent training bouts. And also imagine if there was a competition or match here for this particular athlete. Not necessarily the optimum state for the athlete for competing, right? Because you have a depleted fuel tank. Now compare this to the blue line here. With proper carb intake, you have adequate glycogen refueling, and thus performance during each subsequent training bout could be ultimately optimized and lead to more efficient gains and optimum status for competition, especially if it was performed, like, say, for example, somewhere around here. Now, to summarize these effects for both adequate and inadequate intake scenarios, you can refer to the text right here. So, adequate or high carbohydrate intake will lead to appropriate insulin responses, which would maximize muscle glucose uptake and also be stimulatory to glycogenesis, which would maximize refueling of the muscle. And of course, this should be conducive to optimizing exercise performance. So thumbs up for that. So the opposite would occur with low or inadequate carbohydrate intake as described here. So thumbs down for that. And you can see here in comparison that with repeated training bouts, muscle glycogen levels become more discrepant between adequate and inadequate carbohydrate nutrition. And so if this is like athlete A versus athlete B, and all other factors that influence performance is controlled for somehow, athlete A will be in a lot better position for competition than athlete B. Okay, and this is all mediated by carbohydrate nutrition. Okay, now for our very last training adaptation, we have increased buffering capacity. Now, if you refer back to slide 18, you'll see that this particular adaptation does not necessarily influence one's aerobic power, but does positively contribute to one's performance, especially during exercise close to one's anaerobic threshold. An increase in buffering capacity is primarily intramyocellular buffering, which is the carnosine buffering system, if you remember from part 1. Now, this adaptation is simply an increase in intramyocellular buffering due to increased muscle carnosine levels. That's pretty much what is happening there. Now, here's the main point. An increase in carnosine buffering capacity only aids in exercise tolerance, which can translate to better performance at higher intensities. So in other words, it helps one be more tolerant to the fatiguing effects of hypoxia and the ensuing acidosis. So this adaptation appears to occur with training intensity at or slightly above the anaerobic threshold. So at or slightly above the anaerobic threshold. So high intensity steady state to high intensity interval training modes is where this adaptation may manifest in performance benefits. So this intensity is roughly around 80% of one's VO2 max or heart rate max, but of course this is highly variable among individuals. So it just depends largely on the individual. This is just an estimate. But generally speaking, with even just 2 to 3 bouts per week, you can expect to see an increase in buffering capacity in muscle within about 3 to 4 weeks. So relatively short period of time. So also please take note of this as shown in this box on the right here. This increase in intramyocellular buffering capacity does not afford significant performance benefits to heavy resistance exercise or max workload exercise like sprinting. And this explains why beta-alanine supplementation, which is intended to raise muscle carnosine levels and thus buffering capacity, does not really help in resistance exercise or sprint performance. Now, this is because these exercise conditions particularly are so past the anaerobic threshold, the acidosis created will always exceed the buffering capacities of the muscle, despite how much training you do and how much beta-alanine you consume and how much carnosine levels have improved in your muscles. This is why exercising at 100% VO2 max intensity will never be sustainable. So finally, the last slide of this lecture series. This is a summary of part 2. So first bullet is increased endurance performance or conditioning as a result of aerobic adaptations, which decreases reliance on anaerobic ATP production. Remember, anaerobic metabolism is simply a backup to aerobic metabolism when aerobic metabolism is too insufficient to meet the ATP demand of higher workloads. So there's no such thing as isolated anaerobic training. You just can't do that. That is physiologically impossible. And there's no such thing as increasing one's anaerobic fitness because you are doing some so-called anaerobic training. That makes absolutely zero sense, despite the fact that you will hear or read about it in some type of media or maybe from someone at the gym or someone you know. Second bullet, aerobic power. The two factors of aerobic power are aerobic capacity and anaerobic threshold. I think you guys should know that by now. This is a topic that was emphasized in part 1 as well. Cardiovascular adaptations primarily influence aerobic capacity. Cardiovascular adaptations are the main driver for an increase in VO2 max, which is the measure of one's aerobic capacity. Maximum oxygen consumption rate. Adaptations that happen specifically in the trained muscle, so metabolic adaptations, these primarily influence anaerobic threshold. And the metabolic muscle adaptation that is the prime driver of an increase in anaerobic threshold with training is mitochondrial biogenesis. So obviously with an increase in anaerobic threshold, this is improving fatigue resistance, especially at a given workload that was previously hypoxic and post anaerobic threshold pre-training. So being able to do more work without fatigue, that's the whole point. With that being said, by understanding the mechanisms that drive an improvement in one's endurance or conditioning, these conditioning programs should be near your anaerobic threshold. This is so you can induce sufficient stress, the hypoxic stress, to stimulate adaptations to deal with that stress. So you need to give your muscles a reason to change. That is the most fundamental aspect of any type of training program. If you are doing highly pre-anaerobic threshold exercise, so low to moderate steady state exercise, it must be exhaustive, meaning fuel depleting, glycogen depleting. This is to provide enough or sufficient metabolic stress to elicit adaptation. This is referring to that AMPK mechanism, right? So because you're doing low to moderate intensity, you're not in that hypoxic environment. You're not near that anaerobic threshold. You're also not depleting fuel at a very high rate. So in order for it to be exhaustive to stimulate adaptation over time, low to moderate intensity steady state training needs to be prolonged bouts of exercise. Okay, so long duration. We're not just talking about a 30-minute jog. We're talking about hours and hours of continuous exercise per bout. May not be the most practical for your everyday gym goer or your fitness enthusiast.